Okay, now discuss experiment number 11. The aim of the experiment is to study the relation between frequency and length of a given wire under constant tension using a sonometer. So, what are the apparatus required here? This is the, you can see now, this is the sonometer device. This is a, what do you mean sonometer? Sonometer is a rectangular hollow box with the length is about more than 1 meter length, and at one end of the box, sonometer box, hook is there. On the other side of the pulley is there, frictionless pulley, and here the slotted weights are there, and a wire is passed over it. Here two wooden prism or two edges. You can say that two wooden prism or two edges are there, just to take the length, particular length. This helps to take the particular length. Okay. And the pulley should be completely frictionless. If not frictionless, you can add oil here also. These are the apparatus required for this experiment. Now, we will discuss the theory of this experiment. Suppose the string is fixed between these 2 points. Then when vibration occurs, the fundamental mode of vibration, the frequency of a vibration is given by 1 by 2L into root over of T by L. This is the working formula. What is L here? L is the length of the string. This is L is the length of the string, and L is the length of the string. And T is the tension in the string, and M, the M here, M is the mass per unit length. M equal to mass, this is not mass, this is mass per unit length. Okay, and in the particular case, in the particular experiment, we will take constant tension. We will take constant tension. That the slotted weights are applying here in the term of the hook, along the hook 1 kg attached to the hook along the hook weight and slotted weight is 1 kg initially, and I have added here another 3 kg here. The total is 4 kg. 4 kg means the tension is 4 kg. Weight. 4 kg. Weight. 4 kg weight. They have applied 4 kg mass, but weight 4 kg weight. That is 4 into 9.8 Newton. This is the constant tension they have applied here. And we will change we'll take different frequency. The frequency will take a different frequency. Frequency will change according to change in frequency. There will be length will also change. And here particularly we will draw the relation between frequency and length. From this, when mass per unit length is always constant and the tension is not constant, we have considered here constant tension. E is constant, 1 by 2 is constant. Therefore, for constant tension, that frequency is inversely proportional to length. If T is constant, if tension is constant, then frequency is inversely proportional to length. Therefore, mu into L will be always constant. Frequency to length is always constant. We will take the different frequency for the different tuning forks we will use having different frequency, and for different frequency we will measure the length. As initially we will take 256 Hz of frequency, the lowest frequency. When frequency is lowest, the length will be more. Then accordingly we will increase the frequency. When frequency increases, then length will be decreases, because length and frequency are inversely proportional to each other. Then we will draw the graph for this. That is the frequency. As frequency is inversely proportional to length, we can draw the graph frequency versus length. We can take frequency along x-axis. Mu in hertz and length L in y-axis, L in centimeter. As already discussed here, the length and frequency are inverse proportional to each other. Therefore, when here the frequency increases, when the frequency increases, for lowest frequency, the length is the highest. Suppose this is the highest length, maximum length, and your frequency is lowest. Then when frequency will increase accordingly, the graph will be like this. Frequency increases, but the length decreases. Because frequency and length are inverse proportional to each other. This is called law of length. Frequency is inverse proportional to length at constant tension. This is called law of length. Then, while doing this experiment, what precautions we have to take? That the wire here, the wire used should have constant uniform area of pulsation, and pulley should be frictionless, and you have to check these wedges are touching the wire or not. These precautions you have to take. The wire, the two wedges must touch to the wires, and the pulley should be frictionless, and table should be horizontal. Table should be horizontal. These are the precautions you have to take while performing this experiment. Now, Dr. Rahman will explain how to take the observation. If you take 1 by L, you can see nu versus 1 by L, you can take the graph. This is frequency and 1 by L graph. Okay, this is straight line. Okay, now Mr. Rahman will explain how to take the observations for different frequency, how the length is different. As frequency is inverse proportional to length. Okay, then initially we have to take lower frequency lower, then length will be more. Then we increase the frequency, then length will be decreases. This is the graph here also, that frequency increases, the length decreases. But if you take frequencies inverse proportional to length, but frequency direct proportional to 1 by length. If you take 1 by length here or by axis in centimeter, then it will be straight line. Okay, now I will explain this.
We have two inputs of the different frequencies, starting with 256 or 288, 320 like this. We will try the minimum of the one way to 56 or we will hold the handle and strike the thumb on the rubber pad and take it and try to touch the board with the handle. And to start with, we bring the bridges very close. Now let me strike and check.
We are going to verify the law of length. We know that for a given load or a tension, the frequency of the vibrating wire is inversely proportional to the length L of the vibrating segment. Okay? So, we are going to verify N1 L1 is equal to N2 L2 is N3 L3 and so on. And then when you plot a graph between N and 1 by L, N along x axis and 1 by L along y axis, we will get a straight line. Now, let us start with a constant tension for the wire, that is we are taking a 2 kg load. That means we have put 1.5 kg load and the hanger weighs 0.5 kg, that is 500 gram plus 1500 gram, that gives you 2 kg. So, this is constant and we take the frequency which is the highest, 512 hertz. So, with a 512 hertz tuning fork, I strike it on the pad and then put it on the bridge so that it gives me a maximum sound. I have to adjust the length. So, for that we have two bridges A and B. A is fixed at 30 suppose, and then I gradually move my bridge B to suppose say 45 and then 45.2 then 45.3, and I find out whether the air is in resonance with 512 hertz. And we find that at 45.3, that is at a difference of 15.3 centimeter, it gives a maximum sound. I check it again. I again fix it at 40, the bridge A is fixed at 40, and then I gradually move my bridge B to 55.5. That is 55.4 I check, 55.5 I check, and I see where it gives the maximum sound, and the rider vibrates and it flies off or tries to fly off. So with 512 hertz, I find that the difference 15.5 centimeter is another resonant length. That means it's the second time I am taking the observed length where it is giving the maximum sound. That means the air is in resonance with 512 hertz, the natural frequency of my tuning fork. Okay, so the first resonant length is L1 15.3. Then L2 is 15.5. I take the mean, that is 15.4, and then I calculate the inverse length, which is 0.064984, and then I can find out the calculation of NL, which gives 7884. Then I take again a frequency 480 hertz. I know that when the frequency is decreasing, my length will increase. So if it will be definitely beyond 15.5, that means it will be around between 16 to 17. So I find out that if I take my bridge A, which is fixed at 30, I move my bridge B, the bridge B, that is the wedge shaped bridge B, to 46.8, that means my length 16.8, I get again a maximum sound for a frequency 480 hertz. That means now the air is in resonance and is vibrating with the natural frequency 480 hertz at the resonant length 16.8. I again take second time and my resonant length is 16.6. For 16.8 and 16.6, I take the mean of these two lengths for 480 hertz and I find it is 16.7. Take the inverse length, which is 0.05988, and then find out the NL, which is 480 into 16.7, that gives you 8015 hertz cm. And I repeat this procedure for 426 and 320, and I find the following mean lengths for 426 and 320 as 18.0 and 24.6. See, gradually from 512, when I go on decreasing my frequency to 320, my resonant length is increasing from 15.4 to 24.6. Now I take an unknown frequency. Now suppose I don't know the frequency. Now I find that if it is less, that means I find that the resonant sound or the maximum sound is heard at a length of, if the bridge A is fixed at 30, it is heard at 50. That means B is fixed at 50.5. That is 50.5 minus 30, that is 20.5 is my resonant length. I repeat this again and I find that for 50 it gives you 60.5. So I get a 20.5 mean length for the X sound. Okay, for the X tuning fork, tuning fork whose frequency is to be determined. Now I have already found for the above 4 observation, the mean NL is 7862.45. Now if I know that it is 7862.5 is NL, which is a constant, and then I know the mean vibrating length for the unknown frequency of my tuning fork is 20.5, then X into 20.5 is 7862.45, then X comes as 383.53 hertz. And if I calculate from the graph, that is N along X axis and 1 by L along Y axis, I find that at 20.5 it is giving me around 385 hertz. It is here from the calculated value is nearly 383.5 and the graphical value is 385. So I am very close to the unknown frequency value. This is how we verify the law of length in this experiment. Then the precautions that you have to follow here is that the bridges have to be moved very carefully. At least twice you must observe the maximum sound, and the heavy weight needs to be placed on the hanger to keep the wire stretched. The bridge B needs to be moved gradually so that air is allowed to vibrate in resonance with our natural frequency of the tuning fork. Okay, then the length should be measured from the mark on A to the mark on B. I mean the resonant length L1, L2 that we take for every observation, or for every frequency tuning of the tuning fork. Thank you.